Bismillahirrahmanirrahim. Assalamu alaikum respected teachers and my dear fellows. My name is Aisha Amin, student of MSc final year in organic chemistry, and I am here to present my presentation. Before I start my presentation, I would like to thank Professor Dr. Nasreen Fatma, Dr. Shazia Nizar, Dr. Zulf Iqbal and Dr. Asad Khan Tanuri for giving me the opportunity to portray my talent. Now moving ahead with the presentation, the topic of my presentation is acid base and redox indicator. Some of the contents of these topics are indicators, commonly used indicators, selection of suitable indicator, acid base indicator, theories of acid base indicators, redox indicators, commonly used redox indicators, and conclusion. Now, what is an indicator? An indicator is a substance which is used to determine the end point in a titration. These indicators show different colors at various pH levels, so we can easily determine the end point. These indicators are either weak acids or weak bases. They will show different colors in ionized and unionized form. These indicators are used in dilute solution form. Indicators are selected on the basis of pH change near the end point. Commonly used indicators in acid-base titration. The color change and the pH range of some common indicators are tabulated below. Here is the indicator, its pH range, color in acidic solution and color in basic solution. Indicators used. Selection of suitable indicator or choice of indicator. The neutralization reactions are of the following four types. The first one is a strong acid versus a strong base. For example, methyl orange, methyl red, phenolphthalein, etc. Number second, a weak acid versus a strong base. For example, phenolphthalein, thiamine blue, etc. Number third, acid versus weak base. For example, methyl orange, methyl red, bromocresol green. And number fourth, weak acid versus weak base. For example, mixed indicators. Strong acid versus strong base. pH curve of strong acid, for example, we can say HCl, or strong base. pH curve of strong acid, for example, like we can say HCl, and strong base NaOH is vertical over almost the pH range 4 to 10. So the indicators phenolphthalein pH range 8.3 to 10, methyl red pH range 4.2 to 6.3, and methyl orange pH range 2.9 to 4.6 are suitable for such a titration. Weak acid versus a strong base. pH curve of weak acid, say acetic acid or oxalic acid, and strong base NaOH is vertical over the approximate pH range 7 to 11. So phenolphthalein is a suitable indicator for such a titration. Strong acid versus weak base. pH curve of strong acid, say HCl, sulfuric acid or nitric acid, with a weak base ammonium hydroxide is vertical over the pH range of 4 to 7. So the indicators methyl red and methyl orange are suitable for such a titration. Weak acid versus a weak base. pH curve for weak acid and weak base indicates that there is no vertical part and hence no suitable indicator can be used for such a titration. Titration of soluble carbonates with strong acid. The pH range of indicators. Indicators does not change color sharply at one particular pH, they change over a narrow range of pH. Acid-base indicators, also known as pH indicators, are substances which change color with pH. They are usually weak acids or bases which when dissolved in water dissociate slightly and form ions. Consider an indicator which is a weak acid with the formula HIN. At equilibrium, the following equilibrium is established with its conjugate base. HIN plus water, H3O positive plus IN negative. At a low pH, a weak acid indicator is almost entirely in the HIN form, the color of which predominates. As the pH changes, the intensity of the color of the HIN decreases and the equilibrium is pushed to the right. Therefore, the intensity of the color of the IN negative increases. An indicator is most effective if the color change is distinct and over a low pH range. Theory of acid-base indicators. Two theories have been proposed to explain the change of color of acid-base indicator with change in pH. The first one, OSTWALD'S theory, and the second one, QUINONOID theory. OSTWALD'S theory. According to this theory, the color change is due to ionization of the acid-base indicator. The unionized form has different colors than the ionized form. The ionization of the indicator is largely affected in acids and bases, as it is either a weak acid or a weak base. In case the indicator is a weak acid, its ionization is very much low in acids due to common H-positive ions, while it is fairly ionized in alkalis. Similarly, if the indicator is a weak base, its ionization is large in acids and low in alkalis due to the common hydroxyl ions. Consider the two important indicators, phenolphthalein and methyl orange. Phenolphthalein. pH range of phenolphthalein is 8.3 to 10.0. Phenolphthalein is a chemical compound with the formula C20H14O4, often used in titration. It is an organic weak base pH indicator. In an acidic solution, it remains colorless but turns pink as the solution becomes alkaline, and in a basic solution, it remains pink but turns colorless. Use of phenolphthalein. It is used as an indicator in the titration of a strong acid versus a strong base and weak acid versus a strong base. Methyl orange. pH range of methyl orange is 2.9 to 4.6. Methyl orange is a very weak base. It is a pH indicator frequently used in titration because of its clear and distinct and color variance at different pH values. Methyl orange shows red color in acidic medium and yellow color in basic medium. Unlike a universal indicator, methyl orange does not have a full spectrum of color change, but it has a sharp endpoint. Use of methyl orange. It is used as an indicator in the titration of a strong acid versus a strong base and strong acid versus weak base. QUINONOID theory. According to this theory, the acid-base indicators exist in two tautomeric forms having different structures. Two forms are in equilibrium. One form is termed as benzenoid form and the other QUINONOID form. The two forms have different colors. The color change is due to the interconversion of one tautomeric form into other. One form mainly exists in acidic medium and the other in alkaline medium. Thus, during titration, the medium changes from acidic to alkaline or vice versa. The change in pH converts one tautomeric form into other, and thus the color change occurs. Phenolphthalein has benzenoid form in acidic medium and thus it is colorless, while it has QUINONOID form in alkaline medium which has pink color. Methyl orange has QUINONOID form in acidic solution and benzenoid form in alkaline solution. The color of benzenoid form is yellow, while that of QUINONOID form is red. Redox indicators. A redox indicator is a compound which exhibits different colors in oxidized and reduced form. Redox indicators are pH dependent. For example, redox visual indicators are of two types: self-indicator, for example, potassium permanganate, and external indicators, for example, starch and potassium ferricyanide. Commonly used redox indicators. Indicators used in redox titrations are indicators and its color change in oxidized and reduced form. Potassium permanganate. Potassium permanganate is a versatile and powerful oxidant that can be used to determine many substances by direct or indirect titration. A unique advantage of potassium permanganate is that it serves as its own starch. Starch is often used as indicator for detecting the presence of iodine. When starch and iodine are present together, they form a deep blue starch-iodine complex. The color of the starch complex is so deep that it can be detected visually when the concentration of the iodine is low. During iodine titrations, concentrated iodine solutions must be reacted with some titrant in order, often thiosulfate, to remove most of the iodine before starch is added. This is due to insolubility of the starch triiodide complex, which may prevent some of the iodine reacting with the titrate. Close to the end point, the starch is added and the titration process is resumed, taking into account the amount of thiosulfate added before adding the starch. Hence, from the above information, we can conclude that acid-base and redox indicators are compounds that changes color at a particular pH. They are typically weak acids or bases whose changes color corresponds to the deprotonation or protonation of the indicator itself. That's all from my side. Thank you so much.